All right, so here are some questions. These are not from actual AP exam questions, but these are examples of questions where perhaps a calculator or problems that you can't solve by trying to quickly type it in online. Like, what are the type of questions, particularly for 2020, you guys coming up, right, and doing an online exam, what would it look like? And so these are questions that someone who's an actual reader, someone who grades it and has been around and does all kinds of conferences and leads them and all that, he really thinks that your calculator is going to be useless in 2020. Online will be useless in 2020. They're going to give you questions where having your textbook being online, none of that's going to matter in terms of that. So what are the kind of questions that you can then expect from it? So let's start with some of these limit questions. It says, use the four functions graph below to state if the limit exists or doesn't and what the value would be. So in number one, it says the limit as x approaches infinity of h at g to x. So a little bit tricky, but as always in math, we're going to start inside out. So what's the limit as x approaches infinity for j at x, which is what's the right end behavior? So if I look here, what the right end behavior is to j, look here on the right end. As it goes to infinity, what answer is it getting closer and closer to? And the answer is 2. So I'm going to put that in. So when I look off of h, what I'm looking for is, what's the value as it approaches 2? There should be an x. And notice that it's 2, but it's below 2. So it's like 2 from the left, if you'd like. It's below 2. So I'm looking at 2 from the left of h at x. So here you can see 2. From the left, what's the value that it's approaching comparing to the left? Oh, here, from the left. That's from the right. From the left, what's the y value? So from the left, the y coordinate is positive 3, and you have your answer. So again, a little bit tricky. You couldn't take a calculator or photo math to be able to solve that. This one's going to be a little simpler. What's the limit as x approaches -1 of this function? And again, it's defined like a composite. So first of all, it's a substitution question. So plug in -1. What's the value of f at -1? Where's f again? Here. What is it at -1? What's the value? So at -1, the value is -1. So what's -1 plus 1? And that's 0. So I'm going to write it over again. But this time I'm looking for the value at 0. So when you plug in, I'm just looking at the value at 0. So the value of g at 0, you might think, oh, it's a whole, so therefore there's nothing. But it isn't. There's actually a value for the function above it. So the value at 0 doesn't mean it doesn't exist. There's actually a value above it, and that value is at 2. And you have the answer. What's the limit as x approaches 0 of this? And again, we're going to substitute in. So 0, when I plug in, where's f? That gives me the answer -1. And then -1 plus 2. Oh, sorry, it's not f at that. So when I plug in 0, I get f at 2. And I'm coming from the right-hand side. So if I look at f at 2, what's the y value coming in here? And the answer is 3. Some tricky limit questions, people, to try to like fight your brain through it. Here's number 4. I might do this to see if I have room for it here. So for number 4, you're given these values, and you're given the function values, the x values, the function, and the derivatives, and then find the following. So here it's g at f at x equals 2. So if I'm going to take the derivative of this, there's a rule that I need to follow first of all. So I am going to do this on a separate piece of paper. So for 4a, if I'm going to do this, I need to know the general rule. This is called the chain rule, ultimately, or the general power rule. So this chain rule it's the derivative of the outside times the derivative of the inside. And if I want to find the derivative at a value, so at 2, what I'm going to do is I'm going to find the value at 2. I'm going to plug that in and then look off the chart. So where there's an x, I plug in 2. So first of all, what's f at 2, looking off the chart? So if I look off the chart, when x is 2, f is 3. So I can plug 3 in there. What's the derivative of f at 2? So the derivative is negative 1. And then one last time, what's the derivative at 3 for g? So for 3, the derivative is 6. Nope, derivative is 5 for 3. So you have 5 times negative 1. So using the table of values chart, you get negative 5. 4b. Here you're given a derivative, and do you know the rule to begin with? So g at x times f at x equals 2. So for this one, this is obviously the product rule. What is the product rule? The first times the derivative of the second plus the second times the derivative of the first, and then you plug in 2 wherever there's an x. So follow the rule, plug in 2 wherever there's an x, and then read the chart. So the chart says when x is 2, the g function is 1/2. When x is 2, the derivative of f is negative 1. At 2, the function value is 3, and then the derivative at 2 for g is 4. And that's a perfect answer. 4c. In 4c, you have the derivative, and it's the square root of g at x equals 2. So first step is, do you know how to take the derivative here? So obviously think of this as to the exponent 1/2. What would the derivative look like? So it's 1/2 g at x to the negative 1/2 times the hook inside, which is the derivative of g. So it's the power rule, subtract 1, and then what's the derivative inside is included. That's the tricky part. Now, wherever there's an x, plug in 2, and then look off your chart. You do not need to simplify this. So you have 1/2. Whatever the answer is to the negative 1/2. So the value of the g function at 2 is 2. That's to the negative 1/2. The derivative at 2 for g is 4, and you have your answer. D. In D, you're asked to do the derivative of g at x divided by f at x at x equals 2. So for this one, this is going to be the quotient rule. So we're going to do that. That's the bottom times the derivative of the top. Subtract the top times the derivative of the bottom, and then the bottom squared. Then wherever there's a x, you plug in 2. And then plug in, and then you're done. So the value of f at 2 is 3. The derivative of g at 2 is 4. The value of g at 2 is 2. The derivative of f at 2 is negative 1. And then the value of the function f at 2 is 3, and you square it. Done. So do you know the rules? You can do it. So maybe your summary sheets can remind you what the rules are. Those summary sheets will help you. Having a big thing of notes is not going to help you. So the summary sheets, fine, have a calculator, but you don't need to simplify. Trying to look it up on the internet is going to be a horror. So I wouldn't try to do that. 5. It says for number 5, f is a differentiable function that we don't know it, but we know there's a condition, f at 3 equals 0, and the derivative of 3 equals 2, and we have an ordered pair 1, 3, and then is on a point on this curve, and then find the derivative at 1, 3. All right. So first of all, do you have the ability to take the derivative of something that looks like this and is implicit? So let's write it down. So f at y divided by x cubed subtract y squared plus 8. What's the derivative here? Well, first of all, on the left side we have the quotient rule. So let's do the quotient rule. And every time y is involved, we need a y prime. So it's the bottom times the derivative of the top, and I need y prime attached to that. Subtract the top times the derivative of the bottom, and then the bottom squared. So even though it looks pretty harmless, there's quite a bit into the derivative when it's a quotient rule. On the right, we have 3x squared minus 2y, but it needs a y prime, and then 8, the derivative is 0. So the tricky part was the left part. Then, what values can I get to try to get, my whole goal is to try to get the derivative part by itself. So what kind of things can I plug in at 1, 3? So at 1, 3, wherever there's an x, I'm going to plug in 1. Where there's a y, I'm going to plug in 3. This y prime is what I'm trying to get by itself. But first of all, we're going to get some values. So again, y is 3. So wherever there's a y, we put in 3. Where there's a x, I put in 1. And my goal is to get y prime by itself. But let's simplify this first. Dividing by 1 is not going to be that crazy. What's the derivative of f at 3? Well, in the question it says the derivative of f at 3 is equal to 2. That's just right in the question. Is 2. And then it's y prime. The derivative times 1 doesn't change. So what's f at 3 equal? In the question it says it's 0. So 0 times 1, that'll be done. And then 1 on the bottom. Here we have 3 minus 6y prime. So my last step is just to get y prime by itself. So we have 2y prime on the left side. We have 3 subtract 6y prime on the right. So I'm going to get all the y primes together. So I'm going to add 6y to the other side. So I have 8y prime equaling 3, and then divide. So the answer is 3 over 8 is the answer that you're looking for. Taking the derivative implicitly with different values and different things like that. So there's number 5. Number 6. Let's look at that. We're doing 6 and 7. 2 left. Use the graph and table above to find the following limit. So I'm going to write that down. The limit as x approaches 4, and it's f at x to g at x, subtract 6. And it gives me some values. It tells me that the value at 4 for g is 3. And for the derivative at 4, it is negative 2. So step number 1 is, if I substitute in, because it's a substitution question, if I substitute in and I plug in 4, g at 4 is equal to 3, and I'm going to separate this. So the limit as x approaches 4 of f at x, what does it equal? And so if I look off the graph, what's the limit here as it approaches 4? And so if you just plug in, it's just a substitution question, you can see it's equal to 0. Here we're going to do the same thing with the denominator. What's the limit as x approaches 4 in the denominator? And so if I said, just plug in 4, what's the value of g at 4? Look off the charts, and that 4g is equal to 3, so it's 2 times 3. So that's 6 take away 6, so that's 0. So what do you notice is that it's indeterminate. So we're going to use L'Hopital's rule. So we're going to take the derivative of the numerator. Now, the derivative of 2 times g at x is 2g prime at x, and the derivative of negative 6 is just 0. Now we're going to plug in again. So what's the derivative at 4 for f? So when I look off the graph, at 4, the derivative would be the slope of that line. That's rise over 1. So that's up 2 and over 1. So that answer is just 2. That's the slope there at 4. What's the derivative of g at 4? And that's off the chart. And off the chart, the derivative there is negative 2. And you don't need to simplify it. And you have the answer. So it's kind of the conceptual part, reading table of values and graphs and knowing your rules, that you think that you'd be tested more on, that you couldn't just take a picture or whatever. So number 7. Here's the last one of the review questions. Oh, 8 is. Sorry, and 9. Approximate this using 4 trapezoids whose widths are determined by these intervals. So, can you do the trapezoidal rule? That would be a good question in terms of the calculator and internet may not be as helpful. So we're integrating from negative 3 to 5 this function, the cube root of x, subtract 1/2 dx, and we're going to use the trapezoidal rule. So we're just going to plug in whenever I need to plug in and not simplify it. So the first interval goes from negative 3 to 0. So trapezoid means you start with 1/2. The width of it is negative 3 to 0. So the width is 3. And then the first height you need to plug in negative 3. So the cube root of negative 3 minus 1/2. Plus the second height, you plug in 0. And if you plug in 0, you're just left with negative 1/2. And there's the first one. You're just going to follow that pattern over and over again. So the next pattern will be from 0 to 1. So trapezoid starts with 1/2. From 0 to 1, the width is 1. And then the first height, you plug in 0. We just said that's negative 1/2. The next height, you're going to plug in positive 1. Don't try to simplify it, even if you can. And there you go. We're going to do the next one. Starts with 1/2. How many trapezoids have I used? 1. I've used 2. So we went from negative 3 to 0, 0 to 1. Now we're going 1 to 2. So 1 to 2, the width is 1. Plug in 1 first. Then plug in 2. And we have one more to do. The last interval, 2 to 5, the width is, so start with 1/2, is 3. Then you plug in 3. No, 2 to 5. So you plug in 2, sorry. So you plug in 2. Plus the second height, plug in 5. And you have it. So the pattern of the trapezoid is 1/2, the width, and then you add the 2 heights using the values that you're given. All right, number 8. In number 8, write each Riemann sum as a definite integral. Now, we haven't done a lot of work on this. So if a question is like this is like a very particular skill. Following a formula doesn't fit. Just recently, they want you to write it as an definite or whatever as this integral. So write each Riemann sum as a definite integral, and each definite integral as a right Riemann sum, but do not evaluate. So in this situation, I even feel like doing number 8 with you. But the limit as an infinite sum, a Riemann sum can be written as that. It's just ugly. Now, some things to look at. Know that I want to write it as integration from B to A. That's how I want to write it. So I need to find my bounds using this. So my bounds, if I look at it for this, you'd actually see that B subtract A would equal this number, 3. And that this number here is what A equals. So that means A equals 2, which would mean that B is equal to 5. So it fits it. That's where you would look on the formula in terms of what it would look like. It would have this pattern to it. So 2 is what A is. B subtract A would give me the answer 3. That's where it comes from. So B must equal 5. So what I'm looking at is integrating from, oopsie, this should say A to B. There it is. So this is going from 2 to 5. F at x dx. I wouldn't spend much time sweating that one. Number 9. And if they do a Riemann sum, I don't think they will. I mean, if they do an infinite sum to represent a Riemann sum, ugh. So number 9, you have the integration from 1 to 5, f at x dx. And they said, write a Riemann sum, write that as a Riemann sum. What would that look like? As a right Riemann sum, but don't evaluate. So this one is write it as an infinite sum. So if I have this integration, that could be written as the limit as x approaches infinity of an infinite sum, where you'd always start at 1 to n, and you're just kind of following a formula here. F at 1 plus k, 4 over n, and then 4 over n, where that is your lower bound. That's where the 1 comes from, the lower bound, your A, if you like. And then this 4 comes from subtracting. 5 take away 1 gives you that. Notice it has the same form as above, so think of it as a formula or a template. That's why I hate it. And just plugging into that kind of temp. So it's something you might see, may not. I wouldn't sweat about it. I'm thankful that you are doing your work, that you're trying your best through everything, honestly. That's it. Mr. G Math, over and out. Till next time.